Gnanam Paramam Dheyam. Knowledge is supreme.
In the last lecture, we have discussed very important theorem and we have proved it. However, I want to state it more formally. In the last time, it was more of a discussion form. So, I want to state more formally what we have proved is the following theorem. So, theorem. This is one of the very important step in understanding the Galois theory, especially the Galois groups, so on. So let L over K be a finite Galois extension with Galois group G, which I am abbreviating for Gal L over K, and let H contained in G be a subgroup and with fixed field M, which is by definition fix HL. This is under the natural action of the Galois group on L. This is the fixed points of subgroup H. Okay. Now we are discussing when will M over K be Galois. Then M over K is Galois extension if and only if H is a normal subgroup of G. Alright, so let me sketch the proof the way we proved it. So we proved, proof. I am just writing the important steps which we checked last time. That so first I am proving this way. First we proved this way. That is, we are assuming H is normal. So H is normal. Suppose that H is normal in G. Then we noted that then this fix HL, this is invariant under every element of G, invariant under G. So that means this is a G set. Okay, so that we have noted that, and therefore we consider the restriction action of G on this. So further we noted that kernel of the G operation on this fix. Note that this G operation is not arbitrary G operation, it is induced from the operation of G on L, which is by automorphism. So therefore this G operation on this is by K-algebra automorphisms. That means G to ought K algebra fix HL. We have this operation on this, which is a sub of permutations on fix HL. This operation, the kernel of this operation is precisely H. For this we have noted that, note that for this we have used fundamental theorem of Galois theory. So to check that we have used, so let me indicate how did we check this. This we have checked as follows. So let call H tilde be the kernel of G2 this ought K algebra fix HL. So that means this is all those elements sigma in G such that sigma restricted to the fixed field equal to the identity on the fixed field. And obviously it contains H because every element of H fixes this pointwise. Therefore, it is indeed here. Conversely, I want to prove that, to prove equality here, to prove the equality here, how did we prove? To check the equality here, that is equivalent to checking the fixed fields are same, but which is clearly bigger. This is smaller group, therefore fixed field this is bigger, this is clear, but we want to check equality here, and that we have checked as follows. We have taken an element here X and we want to check it is here. So an element here is H is an element here means that means and I want to check it here. So therefore you take any element in sigma tilde in H tilde, that is then by definition sigma tilde is an element in G and sigma tilde are restricted to the fixed field of H. This is identity on the fixed fields. In particular X is an element here, therefore in particular sigma tilde operated on X is same thing as X. This is since we started with X in fixed field. Therefore this here, but that means, and that we have checked it for every sigma tilde, but that is precisely the meaning of X belonging to this. So that is how we proved the fixed fields are same, and once fixed fields are same, we know there is a one-to-one correspondence between the subgroup and the fixed fields. So this was precisely FTGT. So we have proved altogether that this kernel is precisely H, but then once the kernel is H, what do we get? Then we get an injective homomorphism from G by H to automorphisms as K algebra of fix HL. But this was in our notation, this was M, but this is nothing but the Galois group of M over K, and then the group, this is injective group homomorphism because we went mod the kernel. So therefore we will get cardinality of this quotient group G by H is smaller or equal to cardinality of the Galois group, but this Galois group cardinality is smaller or equal to degree M over K. That is true for any field extension because we know This is by that Dedekind and Artin theorem. Long back we proved it. This quotient group. Therefore, this is cardinality G by cardinality H, but cardinality G is cardinality of this is the Galois group of L over K, and L over K is Galois extension. Therefore, this cardinality is L over K, and H cardinality of H. H was what? H was the group Gal L over M, that is cardinality of this. This is because H is Gal L over M. This is precisely again this equality by FTGT if I like. Therefore, and because this extension is Galois, we have this equality here, therefore this equality here, but this one is same as M over K, because for intermediary field if you multiply this you get degree L over K. So read from here, we have proved this equal to this equal to this less equal to this less equal to this, but this number and this number is same. So everywhere there is equality, therefore we have proved equality here and equality here, but equality here precisely means that M over K is Galois. This was what one implication we had to prove. Conversely, what did we do? Conversely, assuming that, so converse implication is, so this way we are assuming M over K is Galois. So suppose that M over K is the Galois extension, then I want to prove that the fixed field, the Galois group, that is Gal Lm, is normal in Gal L over K. This is what I want to prove. This is our H, and M is precisely the fixed field of H. And we want to prove, assuming it is Galois extension, we want to prove it is this subgroup is normal. All right. So we want to prove subgroup is normal. So I will therefore I will okay. So it's a normal. So and we want to use the fact that M over K is the Galois extension. So it has a primitive element. So since M over K is Galois extension with Galois group H, which is Gal L over M, it has a primitive element. So let Y in M be a primitive element of M over K. So then we know the minimal polynomial of Y over K. We noted in one of the lecture earlier, minimal, whenever this I am applying it to an element Y in L, which is Galois over K. In this situation we have noted the minimal polynomial is nothing but the product Z belonging to the orbit of Y where x minus Z. This is a monic polynomial in Kx, and it's a minimal monic polynomial of Y over K. Y is one of the element in the orbit, so Y is a root. But because it's a Galois extension and this Y is a primitive element, this polynomial splits. So since M over K is Galois, this is very important observation. That is why I wanted to repeat a little bit. So since M over K is Galois, minimal polynomial of the primitive element splits into simple linear factors in M. So, but the zero, I know what are the, in particular all zeros are simple and all of them, so the zeros of mu I k in M, this cardinality is equal to the degree of mu I, and they are all, that means they are all simple and all of them lie inside M. Therefore, in particular the whole orbit of Y is contained in M. So, therefore, for every sigma in G, sigma of Y is contained in M. Therefore, for every sigma in G, sigma of M is contained in sigma of M. But then I can apply the same thing for the inverse. So, that implies for every sigma in G, sigma of M equal to M. So, therefore we have this map gal L over K to gal M over K. This is sigma going to sigma restricted to M. This makes sense. This is a group homomorphism and the kernel is precisely gal L over M. This is a subgroup here. So, this sequence is exact, means this kernel of this map is precisely this. So, this was our H. So, if you call this map as this is a restriction map. So, this is R or rho. This is rho is, so H is, we have proved H is kernel of rho. Rho is a group homomorphism. So, therefore, in particular H is normal in G, because kernel of a group homomorphism is normal. So, we have proved that Galois group of L over M is normal if and only if M over K is a Galois extension. Moreover, in this case, we have an exact sequence of groups. We have an exact sequence of groups. Which one? 1. All the groups are written multiplicatively, so 1 is the identity. So, this is a trivial group. Then gal L over M, gal L over K to gal M over K to 1. Now, let me explain this terminology exact sequence. That means what? First of all, that means, this means three things. Number one, this map, the first map is injective. So, let me give the names now. This is phi and this is psi. So, phi is injective. 2, the psi is surjective. And 3, the kernel here, kernel of psi equal to image of phi. These three things means this sequence is exact. So, this is a quotient group of this Galois group. So, in particular, so I will write in particular M over K Galois with Galois group, which is gal M over K, which is Galois group of L over K modulo the normal subgroup gal L over M. This is what we have proved. This is very, very important. You will see I want to deduce many consequences from here. So in particular, when can we apply this theorem? So in particular, we can always apply this theorem for Galois extensions, finite Galois extensions always with abelian Galois group. Gal L over K. Whenever the Galois group of the field extension, Galois extension is abelian, then we can apply this theorem, because in case of abelian group, every subgroup is normal. Therefore, every sub extension will be Galois extension in this case, and we can apply the above theorem. So for every sub extension M in between, the Galois group of L over M, because this is a subgroup here, this is normal, and therefore this extension is Galois, and the Galois group will be the quotient group. Mod gal L over M, this is precisely the Galois group of this extension. This is very important. And now let me remind you, we have readily one extension here. So let me write it as an example. Remember, for non-zero natural number n, we have considered cyclotomic field extension Q round bracket n over Q. This is the splitting field of the polynomial x power n minus 1. And the roots of these polynomial are precisely the roots of unity. That is why it is called a cyclotomic field extension. And we have seen that the Galois, this extension is Galois extension because it is simple. So this extension is simple. Qn in fact is generated over Q by a primitive root of unity. Zeta n is a primitive root of unity, which has the irreducible polynomial, minimal polynomial of zeta n over Q. We have checked this is nothing but phi n. This is the nth cyclotomic polynomial. Over Q. This is nothing but the product of x minus zeta, where zeta running is the root of this polynomial. It's an element in this group, and order of zeta in that group is n. And we know there are precisely phi n roots. So degree of this phi n polynomial is Euler's numbers phi n's, and we have checked that the Galois group is precisely units in Z mod n. We have checked that gal Qn over Q, this is precisely the units in the ring Z mod n, isomorphic to this. This is what we have checked. For this checking, we need to compute what is exactly the minimal polynomial of the primitive element of this extension over Q, and we did it last time, and then we proved that this is a group isomorphism. So this is an abelian group. Therefore, if I take any subgroup H, so now let me remind you Galois correspondence in this case. That is, we have here intermediary fields. So there are fields in between. So Q M contained in this, they corresponds to, so there is a both ways map. This is Galois correspondence. This is the subgroups of this group now, Z mod n cross. Remember, this group may not be cyclic, but it has subgroups. So this correspondence given any, because we know this is an abelian group, therefore all subgroups H, these are normal, and the subgroups H will correspond to these sub extensions. So therefore I know by above theorem Galois group of M over Q, this is precisely the quotient group Gal Qn over Q modulo the group Gal Qn over M. So this, therefore we got it as a quotient group of this group. So I want to use this to understand the following problem. So now this is a very, very important problem. This is in fact very important question. Which groups, which finite groups occur as Galois groups of Galois extensions L over Q over Q. So far we only know all cyclic groups occur as a, no, that also we don't know. We, of course, we know that this group, for example, Zn cross, this occurs as a Galois group, and also we know that the subgroups of this, we don't know. We only know that if I take any subgroup H here, then this quotient group that occurs as a Galois group of a Galois extension of Q over Q is very important. And let me tell you, this problem is known as inverse Galois problem. And complete answer to this is not known. In general, answer is not known, but some particular cases are known. In fact, this problem is one of the frontline research problem in this field, and it not only involves Galois theory, it also involves the other subjects like number theory, algebraic topology, algebraic geometry, and commutative algebra. So this problem is considered to be one of the very difficult problem, but also it is a very good frontline research area for the young researchers. I cannot say this is a PhD thesis problem. This is much more than that, but it is certainly worth studying this because of its many applications and many connections with the different fields of mathematics. So with this I will stop and next time I will start preparing to show you how we can realize arbitrary finite abelian group as a Galois group of L over Q. Q over Q is very important. I will show you also that if you do not demand this base field to be Q, then it is not so difficult. But for Q it is more difficult, and such fields are also called number fields. So, these are called finite extension, finite field extension L of Q, they are called number fields. So, when can a finite abelian group, when can arbitrary finite group be a Galois group of a number field? That is the main question. And I will show you that every finite abelian group is, we already have enough machinery to show you that every finite abelian group is a Galois group of a number field over Q. And I will show you the other groups like symmetric group Sn or alternating group An, they are also Galois groups of the number field over Q. This I will show you explicitly in coming lectures. That will require some preparation, but it is well within this course and we shall do it. So, with this I will stop this lecture and continue working on this next time. Thank you.